Alright, hello science friends, I'm back again. I've got the second video in our unit 2. This is on gas laws. Okay, so we're going to start talking about how gases are. In the previous video we talked about how intermolecular forces affect solids and liquids. In this one we're going to talk about what makes a gas special, why it's a little bit different, things like that. So I'm going to jump over, I'll go this way this time. I'm going to jump over and I'll come back with, after you write down the notes. Alright. Okie dokie, so hopefully that was enough time. Here are the notes. So we're first going to talk about the ideal gas law. And what's really important here, we're not going to get into really the laws and the math of it yet. But the ideal gas law really is just saying that gases move around in random motion. So they don't follow a certain trajectory, they just move in random motion. And it's a straight line. Okay, so they move in straight line random motion. So if I send a gas particle going off this way, it's going to continue going into a straight line until it hits something. At that point it's going to bounce off in a perfectly elastic collision, meaning it's not going to lose energy. And it's going to start going in another direction. And it's going to keep going until it hits something else and it turns and keeps going. Okay? Kind of like little pinballs in a pinball machine. The other thing it's saying is that the gas particles are so far away from each other, my gas particles are so far away from each other that any small intermolecular force they have, because most gases have at least some small intermolecular force, no matter what small intermolecular force they have, they're so far away that those forces are so weak that they don't affect each other, which is why they travel in random straight lines. Gas particles don't clump together and start doing veering things or attracted, kind of like planets around a sun. They don't do that. It's straight line random motion. Another thing is that the volume of the actual atom or particles we just ignore. That's because atoms are very small and gases tend to be very expansive. So we just kind of ignore the volume of the atom just because it makes math much easier. Alright, so ideal gases stop behaving ideally, meaning that they stop or they become attracted to each other. They stop no longer being attracted. So if they stop behaving ideally, they become attracted to each other when you're getting close to condensation. And that's because the particles start getting closer together. So if I, let's say, have water vapor and I decrease the temperature of the water vapor until I get right around that 100 degrees Celsius mark, that's where it starts condensing and turning into liquid. As the temperature goes down and as those particles start getting closer together, now the intermolecular forces can affect each other, other particles over those shorter distances. So as I get close to the condensation point, my gases behave less like a gas and more like a liquid. And as they pass the condensation point, now they behave only as a liquid and not as a gas. So you can think of it almost like a little gray line. As you pass this, as you get closer to this condensation line, the gases start becoming more attracted. Their motion isn't quite as random. It's not quite a straight line, or straight lined motion. And as they pass the condensation point, now they transition into liquids. So now they can no longer fly away from each other. Now when they come close to each other, they're now attracted and they start to slide past each other. The distances start to become very small. They become very close together. All right. And I just tossed this in at the bottom because it doesn't really fit anywhere else. Let me jump over here. It's the law of partial pressure. All it's saying is that the total pressure in a container is the summation of the partial pressures, or the sum of the partial pressures. So if I have 4 atmospheres of one gas and 5 atmospheres of another gas, and I put them into a container, the total pressure is going to be 9 atmospheres. It's pretty kind of a simple idea. It's going to tie much more into stoichiometry later. All right, I want to talk just briefly about the relationships between pressure, temperature, and volume, because those are important. There's something in chemistry called the combined gas law. It turns out that these 3 variables, pressure, volume, and temperature, are linked together and they affect each other. So for example, let's say I have pressure. Let's say I have the pressure of a gas. If I increase that pressure, if I increase the pressure of that, it's actually going to increase my temperature. They're directly related. So if I increase my pressure, I'll increase the temperature. On the flip side, if I decrease my pressure, then I decrease my temperature. You guys have ever used those canned air that you kind of use to blow out a keyboard, or spray paint, or anything will work, or hairspray, or whatever? If you keep pushing it and having more air come out, the pressure inside the can goes down. And as a result, the temperature also goes down. So the can will actually feel cold. And the opposite is true as well. As I increase the pressure, I increase the temperature. Let's say I have a can of Axe spray, you know, that spray that people love to spray, it's really annoying. I have a can of Axe spray and I increase the temperature of it. As I increase the temperature, I increase the pressure inside that container. And I can actually increase the temperature so much that it will burst. That's why on the can it says do not store in direct sunlight, because the fear is that if you store it in a hot car in direct sunlight, you can increase the temperature so much that the can could burst. I know it's a direct relationship, and mathematically we do that by putting them on a top and bottom of a fraction, numerator and denominator. Therefore, volume and temperature are the same way. So if I increase my volume, I'm increasing the temperature. That kind of makes sense. If I have a balloon, let's say it's your birthday and I have a balloon inside class, and if your birthday is in sad winter, I'm going to walk outside in the middle of winter. The temperature of that balloon will go down, and the balloon will actually deflate slightly. Now the good news is you bring it back into the car, you warm it up, and your balloon will inflate back up. And then last but not least is pressure and volume. Now these, notice they're both on the top of a fraction, so they are actually not directly related like these, they're indirectly related. So as I increase the pressure of a gas, the volume will go down because the amount of space it takes up is less. So if I increase, or let's think about it the other way, might be easier. If I increase the volume, the pressure goes down because now there's more space for that gas. So if I increase the volume, the pressure will go down and vice versa. Okay? So these are the relationships in the gas laws, the combined gas law, the ideal gas law, as well as the law of partial pressure. Hope you enjoyed yourself, and coming back for video 3, which is about Maxwell-Boltzmann curves. Exciting.